4.3, evaluating logarithms. We start off with something that maybe you already know. A common log is log base 10, and a natural log is log base e. Those are important ones to memorize. And when you look at your calculator, those are the only two logs that are going to be on your calculator. You should be able to find a log button and a natural log button on your calculator. Those are the only two. Everything else we're going to have to pretty much change. If you've got a log base 4 or a log base 7 or whatever, you're going to need to change it into a log base 10 or a log base e in order to use your calculator. All right, so we start off with example 1, and it says log of 10,000. Now, since it's log, just the common log, that means you can use your calculator for it. All right, but you might not need to if you remember what a log is. Sometimes you're going to be able to do these in your head. A logarithm is equal to an exponent, right? And so the way you can do this one in your head, log 10,000, is if you understand that common log is a log base 10. And so if you think of it as an exponential, you're looking at a base 10 and you're saying, basically, what is the exponent? So you've got a logarithm is equal to an exponent. And so if you were going to do this in your head, you would say, what exponent would make 10,000? And you should probably be able to do that in your head, but let's say that you can't. Okay, if you can't, on this one, since it's just a log, we can type it in. Log 10,000 equals 4. It's not always going to come out to a nice number like that, but in this case, when it does, maybe you could do it in your head. This answer is 4. The end. All right. So what if I said log 100? Think of it as, okay, I know a logarithm is an exponent. What exponent makes 100? Does anybody know? Very good, 2. It's like 10 to the second power is 100. So really, when I'm finding a logarithm, all I'm doing is finding the exponent. Okay, sometimes you're going to be able to do it in your head, sometimes not. I look at the next one, 341, and if you think of it in that way, it's like, what exponent makes 341? And I can't do that one in my head. I know an exponent 2 would make 100, and an exponent 3 would make 1,000. So in my head, I know the answer is in between 2 and 3 somewhere. All right, that's basically all I can do in my head, but I don't need to do this one in my head because I've got a calculator. Log 341 is 2.53. If it's up to me, we're going to round off to 4 decimals. So 5328. .5328 approximately. Next one. All right. What exponent makes 0.06894? That's a tough one. Does anybody know? Can anybody put it between 2 numbers? Well, it's kind of tough, I guess. So what was it? Lucky for us, we don't need to know this one in our head. Log 0.06894. It's going to be a negative. Negative 1.1615. And think about what happens when we have a negative exponent. Negative exponent flips it, right? So I guess that would make sense. 1 over 10, you know, think about it as a fraction almost. That's how it's going to be a number less than 1. All right, number 2, natural log of e to the 4th. Now remember, a natural log is log base e. So when you're thinking about what is the exponent here, this one's kind of tricky because there's so much going on. But we've got a natural log button on our calculator. So worst case, we should be able to type this in. Natural log of e to the 4th power is just 4. And that should make sense because your natural log is a log base e. So your base e is going to cancel out that e and just give you 4. This equals 4 exactly. Natural log of 341. What that's saying is e to what power equals 341. I don't know about you, but I can't do that. but I don't have to because I can just say natural log 341. 5.8319, so about 5.8319. And one way to verify this is if you take that thing and if you say, all right, what's e to that power? E to that power should be 341. And sure enough, it is, only off slightly because of rounding. So then what about natural log of 0.06894? Negative 2.6745. Okay. Measuring the age of rocks. Exponentials and logarithms have a lot of applications in different areas. Finance is one, in this case, geology, I guess. Measuring the age of rocks. It says by measuring the amounts of potassium-40 and argon in a rock, the age T of the rock in years can be found with this formula. Now, I do want to point out I made a typo. So you need to change this minus to a plus right here. Otherwise, you're going to get an error. It's not going to work out. All right, so that's a plus. And you got this formula for calculating the age of rocks. And essentially, we're just going to plug and chug, but they give us this weird information. It says, example 3, how old is a rock sample in which A equals K? So we look at the formula where we have A and K, and we'd want to plug in. But notice they have in the formula A over K. If you think about this, if this number equals this number, then what would this over this equal? 1, right? So they're telling us A over K is 1 without telling us A over K is 1. It's kind of a trick question almost. A equals K, I don't know what A is, I don't know what K is, but I don't need to. If you have A over K plugged into that equation, whatever their values, it's going to equal 1. So then all we need to do is kind of a big calculator question. We've got 1.26 times 10 to the 9th power times natural log of 1 plus 8.33 times 1 divided by natural log of 2. So you want, like, I would recommend a calculator with parentheses buttons, so you can just type all of it in. I don't like typing in piece by piece by piece. You're prone to round off errors sometimes. So 1.26 times 10 to the 9th power times natural log of, you can probably do that in your head. It's going to be 1 plus 8.33. It's going to be 9.33 right there, right? So can we just kind of shortcut a step? Feel free to type in 1 plus 8.33 times 1, but that's a pretty easy one to do in your head. That's 9.33. And then we're going to divide that by natural log of 2. If you got an error, go back and check your calculations. Keep in mind, if you didn't change that minus to a plus, it's going to be an error. But anyway, that's a pretty big number right there. 405 956 5122. So it's about that many years. I would recommend you look at the number and try to make it make sense. That's million billion. That's 4 billion. That's about 4.06 billion years. You ever wonder how they figure out that such and such a rock is 4 billion years old or whatever? They're using some sort of formula like this. So part B is basically the same thing, except this time they give you this information. Well, A over K is 0.325. We're just going to plug that into that position in the formula. So really, it's just a plug and chug question. We've got 1.26 times 10 to the 9th times natural log of 1 plus 8.33 times 0.325 over natural log of 2. So again, that's just a calculator question. So 1.26 times 10 to the 9th times natural log 1 plus 8.33 times 0.325, close it and close the whole thing, divided by natural log of 2. So once you get all that entered in, we get that big, huge number, which is about 2381840,253 years. About that number of years, which is about 2.38 billion. Change of base theorem, okay? Put a star by this or something, some kind of memo to yourself that you want to have this formula memorized. This is important because notice in example 4, you're going to see a log base 4 and a log base 2. You cannot enter this directly into your calculator. You have to use the change of base formula if you're going to get this answer on your calculator, all right? So use the change of base theorem to find an approximation to 4 decimal places for each logarithm. Log base 4 of 20. Now, I can't do this in my head, but I can get kind of close, I guess, in my head. If you remember that a logarithm is equal to an exponent, right? So think of it this way. You've got a base 4, and we're looking for what exponent gets me to 20. What exponent makes 20? Can you get between two numbers? What's the answer have to be in between? Well, 4 to the second power is 16. And 4 to the third power is 64. It's going to have to be in between 2 and 3. My exponent is going to have to be in between 2 and 3. I can't get too much more accurate than that, but I absolutely know the answer is going to be bigger than 2 because 4 squared would be 16. So it's going to be a little bit bigger than 2. It's a lot closer to 16 than it is to 64. So I think the answer is going to be closer to 2 than it is to 3. But how you would use this change of base theorem is you always go with, notice the pattern, see how this x is on top? And see how this a is on the bottom? Notice that pattern, pay attention to that pattern. You have to put it in that order. So what we're going to do is see how this 20 is on top and this 4 is on the bottom. We're going to use the change of base formula, which is going to say log 20 over log 4. Now what I kind of skipped over is this b right here could be any base you want, all right? But it's useful for me to use base 10 or base E because those are the buttons that I have on a calculator. So really what I'm saying is log base 10 of 20 over log base 10 of 4. I'm letting b equal 10, and that's the way I like to do it. I know other people like to use log base E every time, but I would much rather, I don't know, I just feel more comfortable with the log base 10. So I'm doing log 20 over log 4, and all I'm doing is typing that in on the calculator. Log 20 over log 4. Now remember what we thought the answer was? The answer is going to be between 2 and 3, right? Probably closer to 2 than to 3. 2.1609, oops, round that up to 10. 2.1610. So approximately 2.1610. Remember what we just found. We found an exponent, right? We found the exponent that makes 20. So if you wanted to check your answer, you're saying, well, what's 4 to the 2.1610? 0.096400474. What is 4 to that power? Well, it better be, what did I do? Oh, I missed my 2. Oops. Sorry. 4 to the 2.16. That needs to be about 20, right? 4 to the 2.16 is about 20. Sure enough, we found the exponent. So literally all you have to do once you memorize this formula is just say it's going to be log 7 over log 2. All right, now before we type this in, let's try to do it in our head. You're finding the exponent. 2 to the what power equals 7? Well, I can't do it in my head, but I can get kind of close. What two numbers does it have to be in between? 2 and 3 again, right? 2 to the second power is 4. 2 to the third power is 8. This is closer to 8, so I would expect my number to be closer to 3 than to 2. But we can kind of at least check our answer, I think, in our head. But I'm going to do log 7 over log 2, 2.8074. Now, what happens if I use natural log? Natural log 7 over natural log 2. It's the same thing, and it should be the same thing because the way the formula works, remember when I said b up here in the formula can be anything. So you want to use base 10, use base 10. You want to use base e, use base e. It doesn't really matter as long as you do the big number over the small number, right? The 7 has to go on the top and the 2 has to go on the bottom.